Good morning, good day, and good evening to you all. My name is Wene, and as the introductory said, I am a Professor Emeritus at Chalmers University of Technology in Gothenburg, Sweden. I will talk about learning curves and energy policy, which from a purely economical point of view may turn out to be somewhat controversial. We will come to that later on in my talk. I have two tasks in front of me. Firstly, I should show that the learning curve and learning curve analysis, originally developed for the project levels, work equally well for the level of whole industries and society. And secondly, I must illustrate the use of learning curves for design of legitimate and efficient energy technology policies. So let's get started. And I would like to start from a very basic local project level, a view from the 8th floor. I live myself on the top floor of an 8-story building which is 50 years old. Some time ago I received a message that all the elevators of this building must be exchanged. There are several entrances. Each entrance has only one elevator. There's no way of passing between the entrances. And the team would go from one entrance to another. And the point was it was going to take 3 weeks without elevator service. Now this caused some concern, of course. After 2 weeks, you probably will run out of fresh stock. So after a moment of despair, I said, why don't I turn to my own theory for learning curves? And the first point to make was that the project team, which is going from entrance to entrance, is autonomous. Once it gets started, the team is a master of all its operations. In cybernetic language, it means that the team has operational closure, defined as all effects of the team's operation stays within their network of operations. And then, following this, we can move to my cybernetic theory for learning curves. And the prediction is then that this team would move at a learning rate of 20%, meaning that after each doubling of total elevators exchanged, they will reduce its work time by about 20%. And also importantly, from the team's perspective, the job is unique, so they would really start down the learning curve from day one. Now, the calculations then is pretty straightforward. The 15 workdays, as the 3-week workdays, is only for the first entrance, and that, luckily enough, was not mine. And they would have 20% reduction at each doubling of elevator exchanges. My entrance was number 4, so that meaning 1 to 2, 2 to 4, 2 doublings. So it means I would be down for my entrance to 9.6 workdays. And after 2 weeks of marching up and down the stairs, I moved up to the elevator doors and pressed the button, and there was a slight purr, and then the doors slid open. The learning curve has manifested itself. So what do we learn from this? Well, learning curves measure performance of operationally closed learning systems that act in competitive environments. And what I would like to take with me from this slide is the term operationally closed. It's very important. The fact that you have to also know where the learning curves start, and that in that case, if it's unperturbed, the team will have a 20% learning rate. And above all, it is the team, the human activity system, that is actually learning, not the technology. So we have to talk about learning systems. Now, you could say that my experience is a little bit anecdotal. So let's move to a well-documented case by the Utrecht team, Junginger et al., 2004. It regards a team that was installing wind turbines, offshore wind turbines outside of Denmark. And you see their learning curve there, starting at turbine number 3 and going up to turbine number 80. That is the number of turbines installed on the x-axis. Notice that it is double logarithmic, this plot. And what it shows is the installation time in workdays per turbine as a function of number of turbines installed. That is the cumulative number of turbines installed. And then you go up to the green field above it here, and you find that this curve has the equation workdays per turbine equal to a constant times the number of turbines installed raised to the power of minus E, where E is a constant, which is usually referred to as the experience constant or the experience parameter. The learning rate, to the right there in the picture, has a very simple relation to this, this parameter. And sometimes also in the literature you'll find the progress ratio, which is just 1 minus the learning rate. And the learning rate in this case is, as you see, 22%, quite close to the 20. You can ask yourself now what is actually gained. And it's quite a staggering number. It turns out that the learning effect reduces the total work days by 56%. So instead of having over 200 work days, they did the whole thing is just about 100 work days. It's quite a strong effect. And there's a lot of these types of measurements around. And I would like to show you the next one because it tells you that the learning curve is actually pervading time. Something happened here. There. It shows you a learning curve which is over 200 years old. It is one of the first naval architects in Sweden, Af Chapman, building warships at Karlskrona shipyard, 1782 to 1785. And you have the very nice, once more, the learning curve, with a very typical behavior in the beginning, when you are searching for your routines. And you can see also that that open circle up there, it is he tried to build ships during the winter time in December and January. And of course, he had to spend quite a lot of time on the slips. These, considering the lighting in Sweden without electricity, it would be a very tough job. But in the end, he managed to collect the whole thing very nicely around the red learning curve there. And the little figure, little photo that you have down there, it tells you that if you ever come to Sweden, you could check in at this hotel. The boat is called Af Chapman. It's the name of the architect, the shipwright. And it lies very beautifully on the stream in Stockholm. But it is, of course, not one of the boats he built. It's a new one. So let's move back to our case with the wind turbines at Hornsey. It's quite clear that this learning curve is really a game changer for business. Assume that you were going to bid to be the entrepreneur for this installation. Many would maybe bid on the let's say, the 3 days that you have there for when it starts. But if you really want it, you should place your bid under your cost, under the number of workdays, because you are still going to gain if you have a good confidence in the possibility of achieving the learning for your team. So that would be the red line. And still you would have and harvest more than 50% of the gain of workdays. And you would leave to the consumer the rest. He would get somewhat what you would call the sort of consumer surplus, which is the green field above the red line. And of course, the people or your competitors, they want to have all the green field for themselves. So they would, in American law, maybe charge you in court for predatory pricing because you are pricing under cost. And we are not going into that to show you. And if someone is interested, there's quite an interesting paper by Cabral and Jordan from 1997. So the question now is a game changer for business. Will it also be a game changer for energy policy? Well, we then have to move up from the project level to the industry level and the societal level. And in order to do that, we need some type of leverage. We need some type of major philosophy behind these learning curves. And my proposal is that you turn to cybernetics and make a simple cybernetic interpretation of what you see here. You have a learning system, which is the installation team. You have an input to this learning system, which the one we are really interested in workdays. Of course, there are other inputs like the turbines and so on, but after all, they are not changed by the learning system, so we can look away from them for the moment. And output is installed turbines. And then, very importantly, you have a feedback from the experience of the previous turbine installed back to the learning system in order to improve your installation for the next one. So if you look now at the equation for the learning curve, the left part of that equation is really the ratio between the input workdays and the output of this learning system. And the right part of it is really the feedback to the learning system, the experiences that are accumulated inside the learning system. So there we have a very simple cybernetic model, actually one of the simplest models you can have for learning. And let's try to proceed with this idea. Now, moving to industry level, it's not enough, of course, to just look at labor, which is the workdays. Working and the learning system on the corporate level, on the industry level, will also work with capital, it will work with material, it will work with energy. And in the middle I placed the research and development, which we'll come back to. Is a little bit controversial here, because actually you would expect the research and development to take place within the learning system. This is a point of debate. Myself, I place the research and development inside the learning system, and of course then it's using the labor, capital, material and energy in order to perform the process of research and development. Anyway, you want to cost all this and put it on one single measurement, and that is cost, of course. So your input here would now be cost. The output, if it is just energy production technology that you have there, it will be measured in kilowatt hours. The point is, of course, if you go to energy demand devices, like a refrigerator or a laundry machine, this you really have to think, what is the useful output from that learning system? So you would rather have that measured in some type of index. There is an interesting paper from Lawrence Berkeley from 2013, which you could read a little bit how they handle this problem. And there's also papers from the Utrecht group. The point is that on this level, you will have the learning curve looking like this. It's cost per output equal to a constant times the cumulative output to raised to the minus e. And when you have cost on the left-hand side, you refer to this type of learning curve as an experience curve. That was introduced by the Boston Consulting Group in a paper from 1968. I will continue to use the expression learning curve in this webinar. So let's now move with this into industries in the energy sector, and we will start with wind power. This is a picture from, once more, from the Utrecht group on wind farms. They have looked at wind farms both in the United Kingdom and in Spain. The upper curve is United Kingdom. And so and that is the first observation. On the x-axis, we now have the global cumulative installed wind power capacity. And on the y-axis, of course, it's a turnkey investment cost. And as you see also, now they work in progress ratios. So you see for UK, you have a progress ratio of 81%, which translates into 19% learning rate. And this cybernetic model now shows that the learning system consists both of the turbine producers and the turnkey investors. And the feedback is global wind power investment, because you have the wind power in 2000 had turned into more or less a global industry. So you learn on a global level. Regarding the input, you could think that they really have managed to grasp the cost, but that must be put with a question mark. They have got the cost of the turnkey investment, but the turnkey investors still have to negotiate the price for the turbines that they buy. So you have on the input, you have a mixture of cost and price. And this is a problem that comes with our moving up into the industry level, because it is difficult really to get hold of the exact cost. So in many times we will have to do with price. And if you now go and look at the other industry here, is the industry making photovoltaic modules for solar electricity. In this case, it is they use the price in order to measure what is the performance ratio of the learning system. It is quite a nice curve, at least up till about 2001. It follows the learning curve, the red curve there, very nicely, with a learning rate of 20%. On the x-axis, you have the cumulative global shipments, and then, as I said, you have price on the y-axis. After 2004, the curve is not behaving so nicely anymore, and we will come back to that at the end of my talk, because it's quite an interesting appearance of the curve. You could ask yourself, if you were a policymaker standing at 2002 and thinking, what are you going to do? Shall you continue with your very successful deployment programs, or shall you stop? And you decide maybe to continue. The question is, should you be very nervous in 2006 and 2007? Because it's now that little bubble there is actually quite a lot of money. So I leave it at that at the moment, and we will come back to it when we are ready. The learning system is now the PV module producers. We don't have cost anymore to measure the performance ratio of the learning system, so we have to do with price. Now, let me show you one example from the energy efficiency technology. In this case, it's a learning curve for an enterprise, grafting energy efficient technology. And the graft in this case, the add-on, is a thin coating of gold that you put on the window glass in order to increase the K value, that is to increase the isolation properties of the glass. And so the learning system in this case is the enterprise producing window glass. Now, in this case, you can't say you really had, when this curve starts in 1992, that you have a global industry. The Germans were probably a prime mover here. So in this case, I've used the German sales as for the feedback to measure the learning curve. And also there's something strange with the learning curve. It's not a straight line anymore. It is, and why? Well, the reason is, of course, that you are measuring the cost both of the uncoated glass, it's starting with, and the coating. So you have two learning curves moving at very different, in this scale, at very different speed. The uncoated glass, of course, is at the very tail end of its learning curve. So in this scale that you have down here, cumulative sales in Germany, it hardly makes any difference as you move from about 5 to more than 100 million square meters of coated glass. But the coating, the technology for the coating is quite a new thing. So there you are at the very beginning of the learning curve. So that moves very quickly. So what you're looking at is a learning curve of a compound learning system. The y-axis is interesting also. Here we are actually talking about cost. The reason is that I've received these numbers directly from the CEO of the enterprise. And he didn't want to give the actual cost. So he gave the numbers in an index. But in this case, it really doesn't matter because it measures very well anyway, the learning curve, and actually a learning curve expressed in cost. Now, shall we try to pull this all together? We see that we still have an input and output, and we have feedback. With the feedback in most cases, except when you are in a country which is really a prime mover, you have to look at global activities. And it turns out, and there's a consensus about this also in the people working with learning curves, that you have in a market with which is in equilibrium, you have a constant ratio between price and cost per output. And that is what I try to capture in the equation down now here. It does mean that actually the learning rate is the same, whether you measure it in cost per output or in price. And of course, the prices you can get hold of, and then you can draw conclusions about the learning rate for the cost, as long as you know that the markets are in equilibrium. Now, let us consider this is also this is concessions we have to do in order to work with learning curves on the industry and societal level. So now let's try to make a conclusion, and the first conclusion for a energy policy. And the first very conclusion, the conclusion zero, so to speak, for the policy, is that learning requires market action. It seems rather innocuous, but it turns out that this leads to somewhat controversial conclusions. But before leaving there, it's nice to know that we are actually moving here from the organizational learning point of view of known territory, because the conclusion is fully consistent with theories for organizational learning, and a good exponent for that type of models for organizational learning is the so-called OADI-SMM, standing for Observe, Assess, Design, Implement, and Shared Mental Models. And for those of you who are interested, there is the original paper by Kim, and there is a very interesting book by Espejo et al. From 1996. But let's go back to the policy message and see what that really leads to. Well, it means that cost reductions require government deployment programs. Very important is to observe that all the learning curves that we saw for wind, photovoltaics, and also actually for the German case of the coated glass, were all dependent on government deployment programs. If you remember the photovoltaic, it moved from around $60 per watt in 1976 to today almost less than $1 per watt. And it is quite clear, and you can look at it, that without the deployment programs that has been going on over the last decades for photovoltaic, it would never reach what we have today. You can ask for whatever general measures like green certificates or whatever you can think about. You will never capture something that is starting from a level of $60 per watt and needs to come down under 1 in order to be docked to mass markets. You need the government deployment programs. But then, because these deployment programs will be quite specific, we come to a controversial point, because this means that you have government intervention in the marketplace. And this leads us back to the question, what is the status of learning curves? Can we trust extrapolations from measured learning curves? And this now brings us to the second part of my talk. From this, we have 3 issues actually. You have policy message 0, learning requires market action. You have 3 issues that you have to discuss. The central one is, of course, the one with deployment programs. The left one is the scenario analysis, and then you also have to take up the status of the learning curves. So what are the under-deployment programs? What are the points? The point is, which you already have seen, of course, is a new costly technology need targeted deployment programs to become cost efficient. That's true for the wind, it's true for the photovoltaic. It is also true, for instance, for any types of ocean power or any other new type of renewables that you can think about. It is also true for, as for instance, for the example of the German case, for some of the new, more advanced energy efficiency technologies. But the point is then that the deployment programs, they provide learning investments They don't provide subsidies. And we also have to make sure that, as we will see it, it's quite a lot of money that is needed for learning investments. So the deployment program should stimulate learning investments from private sources and phase themselves out at break even. Let's go see. What about the lessons on scenario analysis? Well, today's learning opportunities decide tomorrow's energy system. And that, I think, is fairly obvious considering my discussion about deployment programs. You have to make you have to provide learning opportunities and provide learning investments for the new technologies in the energy system today in order to get them to ride down the learning curve. Another thing coming up for scenario analysis is that learning curves drastically reduce cost of low carbon scenarios, which we also should expect, looking, for instance, at what we saw for this team installing wind power offshore Denmark. Another thing that maybe is not so immediately clear is that there exists multiple solutions with the same cost, but different technologies, and with the same large-scale effects on, for instance, low carbon. The point is, they have the same cost, but different technologies. So we would say that you have a situation where you have epsilon in cost and omega in structure. We will come back to that point. On the status, however, the mainstream economists lever today a very strong critique on learning curves. They have a weak empirical foundation. They deliver misleading results, or may deliver misleading results for energy policy, and the learning rate is not a constant property. And if this is correct, of course, much of what you argue for deployment programs and scenario analysis becomes a little bit doubtful. So, on the other hand, the cybernetic theory does explain both the learning curve and the observed learning rates. And the conclusion from that is that the learning curve and the learning phenomena is an intrinsic and stable property for human activity systems in competitive environments. And the discussion of all these arguments you can find in a paper that I published. It just came online for about 3 weeks, and you will find that in the reference list that will be provided. So let's start by saying a little bit about the deployment programs and learning investments. Taken as an example, making solar photovoltaic competitive. You have the learning, you have the red curve up there, that is the learning curve, and you have marked with the straight line down at the bottom, which is, observe the logarithmic scale is about half $0.5 per watt. And that is what the solar PV modules have to reach in order to break even and be competitive generally on a mass market. And in order to do that, you have to provide the learning investments, and that's the red area between the learning curve and the line marking competition with incumbent technology in mass market. And that is quite a lot of money. Actually, our policymaker standing in 2002, he still has to provide of the order of $100 billion to reach the break-even. You have to be careful when you read this because it's a double logarithmic diagram. It would look quite differently if you put it in a linear diagram. So this was for the 2002 policymaker quite a lot of work still to do. Now you can ask yourself, we also have R&D. And the first question, what's the relation between R&D expenditures and learning investments? And this is once more taken as an example, the PV modules. The red line there at the bottom is government R&D totally in all IEA countries, which is, I think, more or less a total global investments in R&D from governments. It peaks around 1980 and is always under $500 billion per year. $500 million per year, sorry, $500 million per year. The blue line is the learning investments. And of course, they were very small up until 1995. Around that year, the Japanese, who really led the development here, they started the Japan's rooftop program. And the learning investments, as you see, they are much larger than, very quickly, much larger than the R&D expenditures. This is also learning investments, it's globally, but a major part of this up until 2003 was actually provided by the Japanese program. Then Germany, China, and US came in. So as the curve rises, then you have really a global learning investments. And in the infold there, I made in 2005, I think, sort of prognosis. 35% is assuming that you would continue with the 35% growth in the PV market. I didn't believe in that time, so I also made a curve for 12%. That's a brown curve in the infold there. And the red curve that you see there is just to show you how much a small improvement in learning rates can do. As you see, the 35% curve peaks out at around $12 billion US, meaning that the total learning investments will be of the order of 100 up to $150 billion. And the 12% is actually the surface under the curve is the same. The 35% would make cost-efficient mass markets 2020, the other one the 2040. And when I made this, I was absolutely sure that the 35% wouldn't hold, but boy, were I wrong, because we are actually more or less realizing the blue curve there. And the next gives you a enlargement of that to ponder over. Now, the point is you have to use niche markets to stimulate learning investment from private sources. And that is what the Japanese PV roof program did. And you can read about this in the IEA book from 2000. It's given in the heading there, the pages. The niche market, well, that is market that actually put an extra value of using the PVs. And that is what you can use in the beginning in order to get money from private sources. The curve shows you the success of the first years of the PV roof program, which was terminated in the beginning of the 21st century, started in 1993. The curve is not straight, and the reason is that once more you have the experience curve of some of two different technologies. You have the PV module, of course, and you also have the balance of system. And also, very importantly, what is shown here on the x-axis is cumulative installation in Japan. Now, the contribution to the learning curve also came from outside of Japan during this time. But as you see, the contribution from the taxpayers, which is really the difference between the blue curve and the brown curve here, slightly dotted curve, is about could be kept quite low because of the existence of the niche market. Because still in Japan, where you could use the PVs, solar as a for peak electricity, you should compare with the 1.1 US dollar per watt, which is pointed down at the bottom of the diagram. So using niche markets actually can help you to reduce the money that has to be put up in front by the taxpayers, or also, of course, by if you use feed-in tariffs by the electricity consumers. And the philosophy behind niche markets, challenger and incumbent cost efficiency is actually discussed in a book from IEA from 2003. And I'm not going through in detail. You can read about it in that book. It's just a way of pointing out the principles, how to use niche markets in order to reduce the cost. Because it's only the area marked A where you really have to provide learning investments from taxpayers or from the electricity consumer Okay, let's another interesting point to make here is, of course, that for an energy efficient technology actually provides its own niche market. So this is now the learning curve. The blue line here is a learning curve for it's a learning investments for the coated glass experience in Germany. The red one is the net effect. And as you see the net effect, then you take care of the fact that actually from the very beginning, the energy efficient technology reduces the bill for the consumer. So quite differently from an electricity producing technology. Here you have actually a positive effect on your electricity or district heating bill already from the beginning. And the learning investments are down to zero in 2000, but actually you break even thanks to the increasing energy efficiency. You break even already in 1995. So this is really a bonus for energy efficient technologies. Now let's move on to scenario analysis. This is the effect or the result from a modeling experiment showing effective but alternative pathways for the global electric system. Remember, this was just a modeling experiment we did several years ago, where we introduced learning curves for all the technologies. And what you're looking at as a global electricity system that looks very different from each other. The left one has some wind, but it's mostly based on coal and natural gas combined cycle. The right one has photovoltaics. It is using gas to fuel cells, and you have wind, and you also have a day and night photovoltaic with making hydrogen during the day and burning hydrogen during the night. And the point is, if you look at the total system cost for these two, it is actually more or less, it is the same. The difference is just noise in the modeling experiment. So the conclusion here is that considering total discounted cost over a longer time interval, that is, you put the time horizon beyond the learning investment barrier, as you remember, for instance, from the PV module, you had a barrier of learning investment to climb over before you reached the break-even. So you put your time horizon beyond the learning investment barrier, you will find that you have many very different optimal least cost solutions with identical starting points, identical assumptions on what's going on around the electricity system in this case. But you search quite different solutions, looking very differently, of course. We did this in 1997. It looks very differently as regarding, for instance, carbon emissions, but still exactly the same cost. And that is, of course, a result of the learning curve. So if now you look at, for instance, one of the major theorems about welfare economics, that says that you can with competitive markets always reach the Pareto optimal solution that you want to have for political reasons, for instance. One of the major preconditions for that theorem is that you have, so to speak, a convex set of possible solutions. But what you see here is actually the fact that the learning curve makes the technology set highly non-convex. So it really takes away, if you accept the learning curve on the level of industry, on the level of society, it really is a challenge to this precondition for this welfare theory. And here is, well, this is just the difference between the two, as I said, is that you have a learning investments of $400 billion to produce upfront, and then you will recover those learning investments after you have made the technologies cost efficient. Let us now, at the end, return to the policymaker in 2002. What is his worries in 2006 and 2008? Actually, what you're looking at is no more a fit to a line, to the points that you have there. It's a pure theoretical learning curve, which is fitted only in one point in 1976. So it is with some confidence we can say that you actually in 2010, in spite of what happened between 2002 and 2010, were back on the learning curve that you should expect. And you're actually undercutting it now, and that is because you have, of course, a sort of glut in the production of photovoltaics. So the conclusion here is that actually this is a silicon bubble that you look at, because the industry was running out of silicon. They were riding piggyback from the silicon factories of the semiconductor industry, but this because of all the government deployment programs, uncoordinated, there was a scarcity of silicon. So the industry started, obviously, of course, to build its own silicon factory, the PV module industry. And as those factories came online, the scarcity costs for silicon were reduced. But you had a silicon bubble that actually costed you of the order of $100 billion US. And you could always make the reflection that concerted action among governments, many governments at that time rushing into to make deployment programs for PV modules. If there had been some concerted action, one could have previewed this scarcity and maybe avoid some of this silicon bubble. So the conclusion here is that you do have a cybernetic theory that actually reproduces quite well the observed results from measurements of learning curves. I leave my talk now at this, and just to sum up these final conclusions. Deployment programs, what the learning curve is, it provides legitimacy and also the possibility of really designing efficient programs. Learning investments, legitimate and efficient deployment programs provide learning investments, not subsidies. Scenario analysis, multiple efficient scenarios with very different structure, potentially challenging conclusions in welfare economics. But we somehow also have to resolve the discussion between mainstream economics and cybernetic theory, with different conclusions on status leading to different policy recommendations. And if someone is interested in emerging issues, there is an interesting paper coming from Lawrence Berkeley that look at roadmaps and learning curves, which in my language would be how should we manage radical innovations. But that may be a topic for further discussions and further webinars. I thank you very much for listening in.